Assalamualaikum warahmatullahi wabarakatuh, and good day to everyone. How are you guys doing? So we are going to continue with our new chapter 5, and in this chapter I'm going to divide into several lecture and tutorials. So in this chapter our main objective are going to be able to draw shear and bending moment diagrams using static equilibrium applied to the section, and then we want to describe the relationship between applied loads, shear and bending moments throughout the beam, and finally to be able to use section modulus to design beams. So this chapter are going to be devoted to the analysis and design of beams for bending. And talking about beams, okay, beams are basically the structural members that are used to support load applied at various points along the member. Beams are usually long, straight prismatic member, and industry there were a lot of steel and aluminum types of beams, okay, and there are also timber beams that are widely used in home construction, but recently contractors have been replacing timber beam with steel, okay, due to the difficulty to obtain a good timber beam. Okay, so in most cases the loads are perpendicular to the axis of the beam, and this transverse loading causes only bending and shear in the beam. When the loads are not at the right angle to the beam, the load will also produce axial forces in the beam. So the transverse loading of a beam may consist of concentrated or a distributed load. Okay, so if we can see from here, there are two kind of load that can be applied. One is concentrated load and the other one is distributed load, and we also have one more concentrated moment, but in this chapter we are mainly going to focus on the concentrated load of force and the distributed load of force. So basically the concentrated load will be in units Newton or kilonewtons, and the distributed load will be in unit Newton meter or kilonewton meter. Okay, so there are also cases where we have a combination load of both concentrated and distributed load. So transverse loading of beams are usually concentrated as concentrated or distributed loads. So the applied loads are going to result in internal forces consisting of shear force from the shear stress distribution and a bending couple from the normal stress distribution. So if we can see at this image, okay, the load, either it is a concentrated or a distributed, are going to result in internal shear force, okay, along the cross section of the beam, and also internal normal forces, where these internal normal forces are going to induce a bending moment. So basically any loads applied on a beam are going to result in shear force and bending moment. So the normal stress is often the critical design criteria. So we have learned in chapter 4 the pure bending. So sigma x can be the stress at the beam, can be calculated using the flexural formula negative my over I, where m is the moment, y is the distance from the neutral axis, and I is the moment of inertia or second moment of area, where the maximum stress can be obtained by this equation mc over I, where c is the maximum distance from the neutral axis and m is the absolute value of the moment. So this is going to obtain the normal stress, we are required to determine the location and the magnitude of the largest bending moment. So along this beam, let's say we have a beam of A to B, so we need to identify in which location that the maximum bending moment occur. Okay, is it at the center or is it at point B or point A? So we need to determine the location of the maximum bending moment. Okay, next, the classification of beam support. So beams are usually classified according to the way they are supported. So as shown in this figure, we have two kinds of beam supports. One is the one that we can statically determine, and the other one is the one that we call as statically indeterminate. So for a statically determinate beams, okay, we are going to be able to determine all the reaction forces, okay, that available in the beams. But for statically indeterminate beams, okay, it will be impossible to only use the equation of equilibrium to calculate all the unknowns forces, internal forces or reaction forces inside or along the beam. So let's take a look at a simplified version of this support. So basically, if you look at this image, we have three different kind of support. Okay, the first one is the pin support, roller support, and fixed support. So for pin support, okay, basically the beams are going to be be free to move, okay, or be able to be free to rotate, okay, free to rotate, and basically it's going to be fixed at the vertical and horizontal axis, the x and y axis, and therefore the only reaction forces that we are going to obtain are at x and y axis. So we can say that this is fx, fy. For a roller support, okay, the beams are going to be free to rotate and also free to move along the x-axis, and therefore the only reaction force that we are going to obtain are going to be at the y-axis. For a fixed support, okay, the beams will be fixed at all direction x and y and also rotation. So therefore we are going to obtain reaction forces of fx and fy and also the moment, the reaction moment. So if we take a look at the combination of the support here, okay, so we have the simply supported beam, which consists of a pin support and roller support, and then we have overhanging and cantilever beam, and then we have continuous beam fixed at one end and another one is fixed beam at both ends. So understanding the beam supports are going to help us to identify the reaction forces exist at the pin. So as I mentioned in previous part, so it is very important to identify the the location of the maximum bending moment in order to identify the maximum stress that occurred along the beam. So the usage of bending moment diagram and shear force diagram are going to make the process much easier, and therefore it is very important to understand how to draw or plot the shearing force diagram, or we call as SFD, and the bending moment diagram, or called as BMD. So now let's proceed with the shear and bending moment diagram. So the maximum absolute values of the shear and bending moment in the beams are easily found if the shear force V and the bending moment M are plotted against the distance x measured from one end of the beam. So besides, in this section, okay, in this part, the shear and bending moment diagrams are obtained by determining the values of V and M at selected points of the beam. So these values are found by passing a section through the point to be determined, okay, and considering the equilibrium of the portion of the beam located on either side of the section, as you can see in this figure, figure B here. Okay, let's say we want to find or identify the shear force V and the bending moment M at this point C. So we are going to cut the section from A to C, and we are going to consider the equilibrium of the portion, okay, meaning the equilibrium of the force at X and equilibrium of the force at Y axis, and also the equilibrium of moment. So since the shear force V here and V prime here have opposite senses, so recording the shear at point C with an up and down arrow is meaningless. So unless it is indicated at the same time which of the free bodies AC and BC is being considered. So for this reason, it is very important to have one similar convention, okay, we call as sign convention, where we are going to apply this sign convention for determining the positive or negative direction of the shear force and the bending couples. So basically the sign convention said that the shear V and the bending moment M at any given point of a beam are positive when the internal forces and couples acting on each portion of the beam are directed as shown in this figure. So we have internal forces is in positive shear and positive bending moment. So basically if we take the section from the left, okay, from the left, let's say from point A, okay, so the internal shear force, okay, V are going to be positive, pointing downwards, and the bending moment are going to be positive in counterclockwise. But otherwise, if we take the section from point B from our right, then the V prime pointing upward are going to be positive, and M prime in clockwise direction are going to be positive. So it is just how we look at the section of the beam. So basically we are going to take the beam from the left, okay, but some cases the problems will require us to take the beam section starting from the right. Or we can also say that, okay, say we have two, so this is also positive shear. Okay, so the shear at any given point of a beam is considered positive when the external forces, the load and the reaction acting on the beam tends to shear off the beam at that point as indicated here. So if the beam is being sheared off like this, so we can say that the shear force is positive in that direction. And for bending moment, so let's say we have the beam is being bended, okay, in this direction. So we can also say that the bending moment at any given point of a beam is positive when the external forces acting on the beam tend to bend the beam at that point that the beam are going to be bending upward. Okay, bending upward. So that's it for the first video lecture. So we are going to continue with our tutorial.